I hope you are seeing that I'm making a small request. If there are a few people who are brave enough to turn your cameras on, then I will be able to tell whether I am belaboring a point and need to go faster, or whether I've skipped something and I need to explain further. So Dr. Fox, thank you for showing your courage. And if one or two other people do that, that will be helpful. So let's think a little bit about benchmarking. Why do we do it? Why is it attractive to us? Why do we put time into it? A few possibilities. One is, well, numbers. We like numbers. They're better than feelings. If the computer system is slow, we'd like to have a way to quantify just how slow. Another possibility, as some of you may remember from the days of Watergate, the advice to follow the money. And there's a lot of money associated with benchmarks, especially when you're talking about very large computers, such as the one on the right here, which is part of what was used by the NASA program in the 1960s. And you may recognize some of the others on this screen. Maybe it's the publicity, the visibility, and benchmarks certainly do from time to time draw headlines. But I think the biggest reason, at least for me, is empirical science. Hypothesis, experiment, result. What the heck just happened? Try to figure it out. New hypothesis, which leads you back to the beginning, a self-sustaining cycle. I think that's the big attraction. So let's talk a little bit more about that. And we're going to turn the clock back here to the 1970s and 1980s. Dr. Fox, I compliment you on your sleuthing skills to dig out a better biography than what I wrote. The only thing I put in my biography that I submitted to the conference was a benchmark that I did in the 1970s, but you found out more. When I joined a performance group in the early 1980s, there were people who were very dedicated. They did this empirical work of hypothesis, experiment, result, and it was a lot of fun. We also had the other three things that I mentioned. One way of measuring the frustration on a computer in the 1980s is by counting the footprints on the CRTs. If people are kicking their screens, well, then you know the computer is slow. And so, yes, there are multiple motivations, but the empirical science nature of it was the thing that really kept us going. And really any benchmark, almost any benchmark, can give you that fun where you say, I think it might run faster if I write a new version of this system service, or I adjust how we are laying out, whether we're in a Docker container on the same host or in two different hosts, and maybe if I split the application this way, it'll get faster. Almost any benchmark can give you that fun of hypothesis, experiment, result, and you can measure where different bottlenecks show up and whether the computer falls over and dies. And the wonderful thing about benchmarking is that if you make a terrible mistake and the computer does fall over and die, well, tomorrow is a new day. You can say, let's start over, and the computer does not hold a grudge. Unlike if you're doing this in many other sciences where that just doesn't work. Although the performance group that I was a member of in the early 1980s and the other performance groups around the company were dedicated, hardworking individuals, there were problems. And there were performance groups in all of the computer manufacturers. And if you look around for old computer advertisements, you will find the phrases that I've put on this slide. One advertisement says, enabling the processor to switch and execute tasks more rapidly. and another talks about being 1,000 times faster. But these claims were so vague that they were neither true nor false. You could not falsify one of them, as Philosophy of Science 101 might say. They didn't have falsifiability because they're so vague. They weren't even statements that you could produce evidence for or against. But the big problem I want to talk about, and the title of the talk is based on comparisons. This work that was being done was almost always not comparable. And we're going to use as a case study a 1985 performance guide. Since Dr. Fox has dug out my employment history, he will know which company this is from, but it's slightly disguised here. And the reason it is slightly disguised is because officially this was for internal use only. Now, it was 160 pages, it was glossy, it was typeset. I think that in fact customers saw it. But since officially it is internal use only, that is why I've put slight disguises on it. So the format of this table is that it tells you all the variations on an instruction. It tells you the time. It tells you how much faster it is relative to the earliest system in that group of systems. So for example, this 4.9 here tells us that we can add 2 registers almost 5 times faster than the original computer in that line. This was presented for 6 or 7 models for all of the instructions, running on for 10 pages. So if you were thinking about whether or not you wanted to upgrade to one of the new models, can you do anything useful with this table? Well, you might get a warm, fuzzy feeling that some instructions are 4.9 times faster, but so what? Customers typically did not know which instructions their applications used. And in fact, somewhere along the line, somebody came out with a nice little paper that showed that, yeah, typically customers used the fast instructions for, excuse me, I need to rephrase that. If you looked at all of the instructions in a program, yes, the majority of them were the fast instructions. But the vast majority of the time was not on them. The vast majority of the time was on the slow instructions. And this, of course, varied from application to application. It just didn't tell you the comparison that you needed to know. It doesn't tell you how your application will do, and knowing the instruction speeds doesn't tell you anything about how your application might work on the systems from this company versus systems from some other company. So although these instruction tables had a lot of science and effort behind them, we really needed to have industry standard applications, so-called. And this performance guide referenced probably 50 or 100 so-called, what they called industry standard applications at that time. These are just a few excerpts from it, and these are actual phrases from that performance guide. I did excerpt here. I didn't show you where I omitted words, but it actually said these things. Industry standard Fortran benchmarks have been altered. It didn't say how. Harris test. Many vendors have limited the size of the data arrays. Okay, but it didn't say what size was used in these tests, and it didn't say what size was being criticized. And most wonderfully, if a compiler notices that you are not using the result that you're computing, it is not obliged to compute it. And so a bunch of the benchmarks had 0 time. This is the state of industry standard benchmarking in the early 1980s. So they had the advantage that they were not in assembly. At least they were in a higher level language, in this case Fortran, and some of them C. But as I mentioned as we were walking through it, the exact changes that were made were not clear. And it was also not clear which versions of the benchmarks were used. So if we want benchmarking to be a comparable science, well, these are not comparable. The biggest expense in the performance group that I was a member of in the early 80s was probably the transaction processing benchmarks. I sat next to 2 engineers who worked on something called a remote terminal emulator, which would emulate users typing transactions and be able to have 16 or maybe even 32 simultaneous users. To describe their results, they took 40 pages of detail to lay out the software environment, the benchmark environment, the database environment, the management of the tasks that were handled in a pool of microtasks to be able to do these transactions. And again, though, it was only a single vendor system. And furthermore, the sources were not available. So a lot of work, not very comparable. All right, now we come to something which is a little bit more comparable, whetstone and drystone. At least for this one, the 1985 Performance Guide did reference specific versions. And furthermore, drystone, written by Dr. Reinhold Weicker of Siemens Nixdorf. Drystone actually included a notion of run rules. However, both had several versions. It was not always clear which version was being used. And as Dr. Weicker himself pointed out, they were synthetic. Now, you've heard mention this morning of microbenchmarks. And yes, microbenchmarks, synthetic loops that are very small, have their place. They can show you like a microscope focus on something very specific. But because they're synthetic, it may not be clear how they relate to real applications. So we come at last to SPECmark. And the occasion of this paper, the occasion of this talk actually is it arises out of Dr. Lizzie John's 50th anniversary issue of the microprocessor issue for IEEE Micro. And I contributed to that issue by digging out the original 1989 SPECmark. And so this is the original SPECmark. This is a result from 1989. You can maybe just barely read that on the bottom. And a couple of things to notice about this 1989 result. Number one, and most importantly, there was what was called a full disclosure. You had to say, how did you configure the operating system? What tuning parameters are used? What was the system state? How much memory was on this? Now, over time, this full disclosure became much more detailed. Now, I'll mention that again a little bit later. But this was an amazing start in 1989. Everybody who wanted to publish results needed to provide that full disclosure. And the applications being benchmarked, some of them were still tiny kernels, but there was this movement toward real applications. Benchmark 001.gcc, that was the GNU compiler in all its glory, a real application. And some of the others also were real apps. Some of the other things that improved comparability. SPEC controlled the sources. So if you wanted to know whether or not you were running the same version of Harris test as somebody else, that was hard to tell. If you are publishing a SPEC CPU result, then that was well defined. Dr. Reinhold Weicker, I mentioned, wrote some run rules with Drystone. That was, I believe, an innovation. I haven't spotted other benchmarks from that era that had run rules. Well, Dr. Weicker joined SPEC, and he helped to enforce the run rules. And one of the ways in which the run rules are enforced is when you publish a SPEC result, SPEC CPU result through SPEC, your result is reviewed by other people who also know that benchmark. So a notion of peer review. One of the presidents of SPEC described it as, you know how sometimes when you're doing benchmarking, you might like to tilt the playing field so that you're on top. Well, during review of results, there is a large pile of wolves which are looking to see whether or not you've done anything like that. And they will tear you apart if there's any sign that you have tilted the playing field in a way that is not fair, that's against the rules or against the spirit. And so you won't be able to tilt your playing field, but you will be able to achieve a level playing field because there is this peer review. So that's some of the things that were done as early as 1989 to ensure comparability. But perhaps the most important, did it get the right answer? I can make it run as fast as you like if you remove the constraint that I have to get the correct answer. I emphasize this point because this, I believe, is a fundamental mistake in benchmarking if you don't do this. And there's an extremely popular benchmarking suite which came out within the last, golly, maybe it's 15 years now. I still see it widely used, and none of the answers are validated. And so if a compiler goes down a completely different path because of, say, a round-off error, which sends a branch a different way, and the main loop is exited after 10,000 iterations instead of after 50,000 iterations, and the answers are wrong, no error message is printed. So fundamental to SPEC, starting from SPEC mark 89, validate the answers. So a few words on history. This was a lot of fun. By the mid 90s, the new SPEC benchmarks were widely used. It was fun because the benchmarks are compared to the VAX 11780, and as early as 1989, there were already microprocessors which were 10 times faster than the 1978 VAX 11780. It gained wide acceptance. Here I have some statistics about number of results that have been published with various versions of SPEC CPU. And there were also many other benchmarks from SPEC, which have also published hundreds or thousands of results. Thus, for over 25 years, it has been wildly ambiguous to refer to the SPEC benchmark. There's never been anything called SPEC 2000. The correct form is SPEC, name of benchmark, and year. However, one of the benchmarking lessons that we learned is nobody ever forgets your first name, the first name you were called by. Let's talk a little bit about some of the further evolution. So when I dug out this benchmark suite from 1989, I noticed some things that changed later on. The very first version of SPEC CPU, yes, it had some real applications in it. I mentioned in particular GCC. However, there were also some micro benchmarks. Over time, with the other SPEC CPU benchmarks, the preference shifted more and more toward real applications, and yet that's what this graph is about on the right. So, for example, with CPU 2006, you can see a lot more lines of source code were in there. For CPU 2017, the biggest benchmark in this set is Blender, and that is from the Blender Foundation, and Blender alone is 1 million lines. The GCC compiler alone is 1 million lines. So there's definitely a preference for real applications. The original SPEC Mark 89 had some benchmarks which did not read any input data. If you don't read any input data, then the compiler is entitled to reduce your benchmark to a print statement. Read something. If you're designing benchmarks, read something. There are changes to make it easier to track what people have done. And as I mentioned, full disclosure is good. And as the benchmarks evolved, there have been many more such requirements to disclose more detail. Now, this graph of how the number of lines of source has improved over the years brings up a sidebar. The last time I gave a talk about some of SPEC CPU benchmarks, I was asked, aren't you ashamed of yourself that you're charging money for these benchmarks? No, they didn't actually say it that way. I exaggerate. Maybe that was some of the tone of voice. But the implication was that it's wrong to charge for benchmarks, and in particular to charge so much money. SPEC CPU costs $1,000 retail. It costs $250 for nonprofit and academic. And how can you dare to charge that kind of money, especially given that SPEC CPU includes within it a lot of open source applications? So I take a moment to respond to that. I should say that I do not set the price. I am not a member of the committee that sets the price, but I did talk to them before coming to see you, and they did say that, yep, I'm authorized to tell you the following things. So first, as a reminder, yes, SPEC CPU draws on open source apps, but those apps remain open source and they are freely redistributable. SPEC values the academic community, has heard comments regarding pricing, and SPEC will reduce the price for SPEC CPU 2017 substantially soon. So that's a sidebar on pricing. All right, I'm just going to sail through this next part pretty quickly. This was written in response to Professor Lizzie Johns pointing out that it took 10 years in between SPEC CPU 2006 and CPU 2017. What took so long? I highlight a few things that took so long because as you are developing other benchmarks, perhaps some of these will be of interest to you. If you're going to parallelize, it's useful if you pick your targets early. We wasted way too much time arguing about what technologies were acceptable for SPEC CPU. Now, I acknowledged earlier that micro benchmarks, kernels, they have their place, but in the SPEC CPU set, that is just not the preference. One person submitted 11 small candidates. None of them survived the final cut. So micro benchmarks, probably not worth submitting to SPEC CPU because SPECs just doesn't tend to want to include micro benchmarks in the CPU suite. There are many arguments about how big is too big and how long things should run. There were many difficulties with validating benchmarks. If you use your eye, do you think that there's something wrong with the picture on the right? It's supposed to look like what you see on top. A particular computer was printing out what was calculating what you see on the bottom. Yeah, it's not supposed to look like that. So it's easy for a human to tell this. It's a little harder to find a way to measure it, but eventually we started using a SSIM method, and that's used for several benchmarks to validate. Portability. If you want to be able to compare, then you want to be highly portable. One set of benchmarks were submitted by one user that had 17 benchmarks, and he said they're highly portable. Well, yes, they were highly portable across various kinds of hardware, but only if you used Linux and only if you used GCC. So those are wonderful things to use, but SPEC CPU does try to hit a wider target of additional operating systems and additional compilers. Licensing. It's important. Take time. Take the time up front. Apply. There are recurring benchmarking pitfalls. Benchmark candidate is drawn from a library. The library is complicated. It's got hundreds of functions, and it turns out that the benchmark candidate doesn't really measure very many of those functions. In fact, what it's really measuring is the time it takes to set up the benchmark. So there's a list of good and bad benchmark characteristics that you can find at the SPEC CPU 2017 pages. One of the hardest. Say you've got this good, comparable, objective, highly portable application, which is a real application that you've made into a benchmark. What else do you need in order to vote for it? If you are a member of the SPEC CPU subcommittee, what else do you need? Do you care about whether or not it's a state-of-the-art algorithm? If it's an algorithm which is a few years old and it's kind of not the latest, greatest thing, does that mean that the benchmark is not useful? If the benchmark is kind of small, but the author is a well-known expert and brings that level of knowledge to this benchmark, does that count for something? If it makes compilers fall over, how important is that? The point here is that subjective criteria are inevitable. Don't wait till the end to figure them out, would be the suggestion. So I end with pointing out that there is a search program underway for the next SPEC CPU benchmark. It's called CPU V8 for now. And one of the ways in which we tried to respond to all of these lessons were we set objective criteria. For example, these sections here, 3C, 3D, 3E, they'll tell you the answers for how much time it's supposed to take and how much memory it's allowed to use and what parallelization technologies are expected to be tested. Those are all objective. But then the last step is subjective. And the intent is to draw out the subjective criteria. So if you submit a benchmark candidate, it's conceivable it could pass all of 3A through 3G and get the monetary award for step 3G, but not move on to step 4. So we've separated the objective and subjective criteria. I think I just mentioned that we've tried to specify these things up front, and it's not too late. If you have an application in mind that you think belongs in a SPEC CPU benchmark, fill out the entry form, tell us by early next year. So I thank you for your time, and we'll happily take some questions.